The picture in the background, I threw that in for you folks to ponder. There's an old saying from the past, gold is where you find it. And that statement has never been so true. That dried up creek bed is an example of discovery. No roads in, no roads out, and you can't even fly in. Just 20 kilometers of backpacking and bushwhacking. Okay, enough of that. In parts 4 and 5, I introduced you to the reagents that are used to make the flux that is mixed with the samples for fusion. These reagents have reactions with your ore material which results in the pre-concentration, collection, and the eventual refinement of your precious metals. In order to effectively calculate the flux requirements, you need to know the characteristics of your ore. Welcome back. I'm Rob Boyko, Boyko Mineral Exploration. As small miners and prospectors, you are probably familiar with the term free milling. For those that are not familiar with the term, it simply means that the gold in the rock's matrix can be liberated, that is, separated from the rock by crushing and or pulverizing it, followed by panning, sluicing, or other methods such as the use of a shaker table, etc. Free milled gold is also known as placer gold. The flakes, flour, nuggets, pickers, etc. have been liberated from the parent rock through the process of erosion and deposited by natural forces. The three examples shown are all free milling ore specimens. The bannerite is sometimes confused with chalcopyrite. It is sometimes worth having that Audubon field guide to rocks and minerals handy. That $30-some-odd book from your local bookstore can be a valuable asset. Regarding placer, and especially you hard rock miners and prospectors, most of you will overlook these refractory ores. My recommendation is don't. Refractory ores such as the one shown, these rock types may in fact be valuable. The gold that these rocks contain is locked in their matrix at the microscopic and molecular levels. The gold that is trapped in these ores cannot be liberated by the usual way that the free milling ores are treated. The gold is contained in the crystalline structure of the sulfide minerals. The gold can, however, be somewhat liberated if the material is roasted. This is a process of heating material to a point where the sulfide complexes are volatilized, but this creates a lot of toxic sulfur dioxide gas in order to form the water-soluble sulfates. Using crucible fusion and lead collection is one method if concentrations of the gold is high enough to recover in any quantity. However, the ore may still be valuable. Take samples and send them out for analysis. Gold concentration can be as high as a couple hundred parts per million for pyrite and chalcopyrite, but it has been reported that concentrations of gold in arsenopyrites have been as high as 10,000 parts per million and more. To a processing plant, these concentrates can be profitable and will purchase this material based on concentration per metric ton. In retrospect, 1 part per million is the same as 1 gram per metric ton. 10,000 parts per million is equal to 10,000 grams per metric ton, or 342 troy ounces per assay ton, or 342 troy ounces per the 2,000 pounds. As stated in the slide, an ore is a natural aggregation of minerals from which a metal or metallic compound can be extracted for refinement and profit. As for the gold miners, you appear to be interested in the gold-bearing ores only. However, for you prospectors out there, do not overlook the other valuable rocks. But not all of these deposits can be classified as an ore. The concentration of the elements that you're interested in may not be sufficient in quantity to actually be an ore. You may find a body of material that contains only a gram or two per ton. It would not be worth your while to mine and therefore not an ore body, whereas 100 grams per metric ton may be worthwhile and therefore an ore body. The A and B group concept is important in terms of pre-concentration and collection. Your ore will have two groups of material constituents. The first of the two groups, Group A, will contain all the wanted metals of interest that you are trying to collect. For the gold miners, it would be your gold, silver, and the platinum group metals. Group B will consist of all the unwanted or material of non-interest. This would be the gangue material. In summary, Group A will be your lead button, and Group B will be the slag. In the Group A category, you will find some native metals, such as gold nuggets, flour gold, pickers, silver, and even platinum. For a prospector, you can also find the native materials such as native copper, native iron, and others. However, these native metals are rare in occurrence. Those that are mostly found is the gold, the silver, and some of the platinum. For the oxidized mineral category, you will find the sulfates, the oxides, the carbonates, and more. The third category would be your sulfitic minerals like your tellurides and arsenides, such as the arsenopyrites. In the Group B category, regarding fusion that is, the slag is referred to as Group B. Your ore or ore samples will contain the Group B constituents. Your slag will contain the silicates such as pure quartz or from the rocks that contain quantities of quartz in their makeup. It will or may contain some of your basic materials such as limestone, magnesite, oxide of all the unwanted metals. There may be silicates such as alumina clay material cemented with quartz. There will be the sulfide minerals as well, such as copper, lead, and zinc sulfides. To a prospector or a large-scale mining outfit, the sulfide base metals may also be considered as Group A material. That's what they're looking for. An example would be a large-scale gold mining operation where the gold would be extracted for the profit and the copper sulfide would be refined from the slag or tailings and sold to offset the operating expenses. Many times the gold and the silver is extracted as the byproduct. Every chemical reaction will create some form of a product. In regards to the fine art of fire, during the fusion process, the reaction between the sample or ore concentrate and the flux, the product created should be a slag full of gangue material and a lead button. The lead button is produced by reducing the lead oxide to elemental lead. If your ore sample during fusion does not produce a lead button, the ore is said to be neutral. A neutral ore is classified as being neutral or class 1. The double-pointed arrow in the equation simply states that this is an equilibrium reaction, where the lead oxide is reduced to elemental lead, but the lead is oxidized to lead oxide, and this reaction just keeps oscillating back and forth, signifying that there is no oxidizing or reducing power of the ore or sample. For an ore to be classified as class 2, it must have some reducing power to reduce the lead oxide to elemental lead, which is what is desired for the collection of the noble and precious metals. Class 3 ores are oxidizing. They inhibit the formation of the lead button. These ores have the tendency to want to give up their oxygen atoms instead of wanting to liberate an oxygen atom from a compound. It is important to realize that the classification of ore material is in reference to the lead oxide and the elemental lead. This is what the charge calculations are mainly based on and will be discussed in detail in a future presentation. Class 1 or neutral ores are those that comprise of the silicates, carbonates, and aluminates. These ores will not comprise of sulfides, arsenides, antimonides, and tellurides, as well as a few others. These ores are ones that are at their lowest oxidizing states. The equation shows that zincite reacts with lead oxide. As the oxygen atoms liberate from the compounds during the reaction, they will recombine. Neither the zincite or the lead oxide is reduced. There is no end product. The zincite, being the ore, does not have any reducing or oxidating power. Zincite is a neutral or class 1 ore. Class 2 ores are those that have some reducing power. These reducing ores will contain the sulfides, the arsenides, the antimonides, and the tellurides, as well as some carbonaceous matter, such as coal, as an example. These ores will also contain elements that interfere with the gold and silver assays. Elements such as selenium, tellurium, nickel, and copper are the most common. In order to collect the contaminants in the slag, additional lead oxide is added to the charge. This will be covered later in another presentation. The example equation shows the reaction with tellurium. The lead oxide is reduced to elemental lead. The oxygen atom combines with the tellurium and the sulfur atom as well, which forms a sulfide ion. Notice the amount of lead oxide required for the reaction in order to produce one tellurium oxide compound. The tellurium oxide and sulfite will be fused in the slag. The example equation is balanced. Since 4 oxygen atoms were required to complete the reaction, there had to be 4 oxygen atoms between the reactants. In order to complete the reaction, 4 lead oxide molecules were required. It can be said that the tellurium sulfide has a reducing power of 4, since 1 molecule of tellurium sulfide is able to reduce 4 molecules of lead oxide to 4 atoms of elemental lead. More on reducing and oxidizing powers in an upcoming presentation. These ore types have a higher state of oxygen levels, meaning that their molecules contain 2 or more oxygen atoms that can be readily or easily released to react with another element. This ore type will not contain any silica. In this slide, hematite is used as a reaction example. This is also a balanced equation, as we have 3 oxygen atoms and 2 iron atoms making up the hematite molecule. The products must contain the same number of constituents. In this example, the hematite will lose 2 of its oxygen atoms, thereby oxidizing the elemental lead. The end result is 2 molecules of iron oxide and 1 molecule of lead oxide. It is for this reason, mixing hematite with lead oxide, any formation of elemental lead would be inhibited. As shown, this is a single reaction equation. The reaction, given enough elemental lead, will result in a second reaction. Combined would result in a double reaction equation. Almost all of the sulfide, carbonate, and oxide ores will break down into a single neutral molecular compound. There are some exceptions, such as the cinnabar, which will volatilize and escape as a vapor or gas. Argentite, under the right conditions, will reduce to elemental silver, and there is bauxite. A simple example to demonstrate this reaction is the reaction of a sample of galena mixed with flux comprising of lead oxide and sodium carbonate. The sodium carbonate is reduced to disodium oxide, which becomes a neutral compound. The galena is desulfurized to elemental lead, and the sulfur is oxidized to a sulfite. The remaining is expunged as a carbon dioxide gas. Note that the sodium carbonate has been reduced to disodium oxide, which is a stable and neutral compound. If you have been following along from part 1 of this series on the fine art of fire, you should have a good picture of what is unfolding. When I stated that those that post videos on fire assay, they do not give you all the necessary information. It is a complex process, and at the same time an easy process if you understand the reactions taking place. By knowing what is happening and doing the right calculations, your losses will be cut down significantly. In this series, I am trying to break it down into little steps so that it will not be too confusing for the average person to understand why the calculations are necessary for a successful fusion and subsequent refinement of the gold, silver, or platinum group metals that you wish to reclaim or recover. By now, you have been familiarized with the fluxes and what they are used for. And then in this presentation, I introduced you to a little more chemistry involving the ores that you may be mining. This is more important to you hard rock miners and prospectors, as you need to know what you have and how much of it. In the next presentation, I will be digging deeper into the reducing and oxidizing powers of the material that I have just covered in the last few presentations. And I will also be discussing some of the intricacies regarding crucible fusion. I hope to see you at the next presentation. I would like to remind you that my channel is not a commercialized channel. It is for education only. I do not promote product, only mining and prospecting for the small-scaled enterprise as well as for a hobby. If there is any advertising, it's beyond my control. I would like to give you a big thank you for watching. If you liked this presentation and found it interesting or useful, please give it a thumbs up and a share. That would be my reward, and please leave a comment, as I do want your thoughts, bad or good. I'm Rob Boyko, Boyko Mineral Exploration.